Introduction to Differential Equations. Welcome, everyone. Today, we are beginning a new and exciting chapter in your mathematical journey, the Introduction to Differential Equations. Now, before we dive into the new material, let's take a moment to reflect on what you already know. In your previous studies of algebra and calculus, you have spent a lot of time solving equations where the primary goal was to find the value of an unknown variable. Such as x or y, you were essentially looking for a specific, fixed number that makes the equation true. However, as we enter the study of differential equations, I want you to prepare to shift your focus. We are moving beyond simple arithmetic values. In this topic, instead of searching for a specific number, our ultimate goal is to search for a function. This shift from finding a single value to finding an entire mathematical relationship is the fundamental difference you'll need to keep in mind as we move forward. Understanding the basics, variables. Now, before we move on to the formal definition of a differential equation in the next slide, we need to make sure we are clear on the two types of variables we will be working with. First, we have the independent variable. Think of this as the driver of the equation. It is the variable that changes on its own, without needing anything else to influence it. In most of the problems you will encounter in high school mathematics, we usually represent this variable using the letter x, or sometimes the letter t, which stands for time. Next, we have the dependent variable. As the name suggests, the value of this variable depends on what is happening with the independent variable. We typically represent this using the letter y, or sometimes the letter p, often used for things like population. To make this concrete, let's look at a real-world example. Imagine we are studying how the position of a moving car changes as it travels down a road. In this scenario, time, which we represent as t, is our independent variable because time marches on regardless of the car's movement. The position of the car, which we will call s, is our dependent variable, because the car's location is entirely dependent on how much time has passed. Understanding this relationship between what changes independently and what changes as a result is crucial, because as we will see in a moment, differential equations are all about how these variables and their rates of change interact. What is a differential equation? Now that we have established the difference between independent and dependent variables, let's bring it all together to define our main topic. So, what exactly is a differential equation? At its core, a differential equation, or we can simply call it a DE, is a mathematical equation that relates one or more functions to their derivatives. To make this a bit easier to visualize, let's break it down into its essential ingredients. For an equation to be considered a differential equation, it must contain three specific things. First, it needs one or more independent variables, like the time t we mentioned earlier. Second, it must involve one or more dependent variables, such as our position, say, or population, p. And third, and most importantly, it must include the derivatives of that dependent variable with respect to the independent variable. If you were reading this in a textbook, you might see a more formal definition. It would state that a differential equation is any equation involving the derivatives of one or more dependent variables with respect to one or more independent variables. Essentially, if you see a derivative symbol in your equation, you are no longer just looking at a static relationship between numbers, but a dynamic relationship between a function and how it changes. In the next slide, we will compare this directly to the algebraic equations you are already familiar with to see this difference in action. Differential equations versus algebraic equations. Now that we have defined what a differential equation is, let's put it into perspective. To truly grasp the fundamental difference between what you already know and this new topic, let's compare a standard algebraic equation with a differential equation. First, let's look at case A, which is an algebraic equation. Take a look at this equation, x squared minus 3x plus 2 equals 0. If you look closely at the components, you'll notice our observation here is that the equation contains only the variable x and some constant numbers. Our goal when solving this is very straightforward. We want to find the specific numerical values for x that make the equation true. As you might remember from your algebra classes, the solution is simply x equals 1 or x equals 2. It's a specific, finite answer. Now let's shift our focus to case B, which is a differential equation. Consider this equation, di over dx plus y equals 0. If we perform our observation here, we see something much more complex than the first example. This equation contains our dependent variable y, our independent variable x, and, most importantly, the derivative di over dx. Because a derivative is involved, our goal changes entirely. We aren't just looking for a single number anymore. Instead, we are searching for a function where y equals f of x that satisfies this specific relationship. As you can see in the solution provided, the answer is a function, such as y equals c e to the power of negative x, where c is a constant. Notice how this is a formula that describes a behavior, rather than just a single numerical value. This distinction is the most important thing to keep in mind as we move into our next example regarding population growth. Real-world application, population growth. Now that we have established the theoretical difference between algebraic and differential equations, let's look at why this matters in the real world. You'll find that differential equations are used extensively in science and engineering because they are the perfect tool to describe rates of change. To make this concrete, let's walk through a classic example, simple population growth. Imagine a scenario where the rate at which a population grows is directly proportional to the current size of that population. It sounds a bit abstract, so let's break this down step by step to build our equation. First, we need to identify our variables, just like we discussed in our second slide. Let p represent the population, which is our dependent variable, and let t represent time, our independent variable. Next, we need to express the rate of change. Since we are looking at how the population changes over time, we write this as the derivative of p with respect to t, which is written as dp, dt. Third, we apply the specific condition given in our problem. The problem states that this rate of change is proportional to the population. P to represent this mathematically, we introduce a constant of proportionality, which we'll call k. Finally, we can formulate our equation. By putting it all together, we get dp, dt equals kp. Now take a close look at this resulting equation. dp, dt equals kp. Notice that it contains a derivative. This, by definition, is a differential equation. As we'll see in the next few slides, our goal here isn't to find a single number, but to find a function, p of t, that describes exactly how the population behaves at any given moment in time. Key takeaways. First, remember that the defining feature of a differential equation is the presence of a derivative. If you don't see a derivative, like di dx or dp dt, then you are simply looking at a standard algebraic equation, not a differential one. Second, I want you to keep this distinction very clear in your mind. When you solve an algebraic equation, like the one we saw earlier where x squared minus 3x plus 2 equals 0, your answer is a specific number, like 1 or 2. However, as we discussed when looking at our population growth example, the solution to a differential equation is not a single value, but an entire function. We are looking for a formula that describes how a variable behaves over an interval. Finally, always remember the core purpose of these equations. They are tools used to describe the relationship between a quantity and its rate of change. They allow us to model how things evolve over time. All right, let's wrap up this introduction by summarizing the most important points we've covered today. Now, before we move on, let's take a moment to look at some common pitfalls that students often encounter when they first start working with these equations. Common mistakes to avoid. First, be very careful not to confuse the variable itself with its derivative. A common mistake for beginners is to treat di dx as if it were just a simple fraction of two separate numbers. It is crucial to remember that di dx represents the slope or the rate of change of the function y with respect to x. It is a single mathematical concept describing how one thing changes in relation to another, not just two numbers divided by each other. Second, try to avoid the habit of looking for a numerical answer. In our earlier slides, we looked at algebraic equations where the goal was to find a specific value, like x equals 1. But as we discussed with the population growth example, when you encounter a differential equation, do not try to find a single value for x or y immediately. Instead, keep in mind that your goal is to find a general formula, a function, that describes the behavior of the entire system over time. Now, as we wrap up this introduction, I want to highlight a few common pitfalls that students often encounter when they first start working with differential equations. If you can keep these two distinctions in mind, you will be well on your way to mastering this topic.